In this video, we're going to discuss how to switch your OMNISEC system from mobile phase to mobile phase. And I want to talk through first some of the areas of risk and main considerations, and then a list of the steps that you take to switch from mobile phase to mobile phase before moving into the video demo. So the main things to consider when switching between mobile phases is firstly that you always want to switch between pure solvents. So always wash out all the salt in your system before switching solvents. This avoids the risk of any salt precipitation, which could cause blockages. So if you're running a mobile phase with salt in it, some aqueous buffer for instance, you want to wash all the salt out and move to pure water before switching to the next solvent. So always follow the sequence of moving from a salty solvent to a pure solvent, to that pure solvent, then switch to your new pure solvent, then add salt, and then you're ready to run. This will prevent the risk of any salt precipitation and any blockages. Now, in order to make sure that detectors get fully flushed, you need to be mixing miscible solvents. So always go from a miscible solvent to another, to a solvent with which it is miscible. If two solvents do not mix properly, choose an intermediate and then move first to the intermediate and then from the intermediate to the new solvent. And acetone works as a very good intermediate that is miscible with most solvents. Now, the viscosity difference between different solvents can put a big strain on the viscometer and can, if you're careless, cause damage to the viscometer. So make sure you flow the new solvent through the detectors slow enough that the DP signal never goes over 5,000 and that the IP signal never goes over 100. So to do this, just make sure the flow is slow. So if you run at say 0.2, 0.3 mils per minute, that'll be ideal for switching the solvent slowly and protecting the viscometer. And we'll see why in the video how big viscosity differences can put a lot of strain in the viscometer. Finally, always make sure that you fully purge the detectors before moving on to the next step. Without doing that, you risk leaving some salt in there that might precipitate or some immiscible solvent. Of course, if you aren't sure, email us and ask for help. Now, the key steps to making the switch are listed here, and this is what we'll be running through in the video, but in summary, they form these steps. So start a baseline monitor. Always be collecting a baseline so you can see exactly what the detectors are doing. Stop the flow. Switch the mobile phase bottle. I'll assume that you've already removed the columns, as we wouldn't switch mobile phases when there's columns present. We would always do that. I'll do the columns separately and do the system separately. So switch the mobile phase bottle, open the purge valve, prime the pump, close the purge valve, start the flow at say 0.2, 0.3 mils per minute, and give it some time. So watch the baselines and wait until they've stabilized. The DP in particular will show quite a large signal for a period of time during which the delay columns are filling up, and it typically takes 10 to 20 mils for that period to pass, which is going to take you 30 to 90 minutes of flow. After that time, the DP signal will return to its starting point. In the meantime, prime the autosampler with new wash fluid. Now, once the DP is stabilized, you can increase the flow to your normal run rate, say 0.5 or 1 mil per minute, and then purge out the detectors. Purge the RI, then zero the RI, then purge the DP, and purge the IP. Once those are finished, you can allow your detector signals to equilibrate, install the appropriate columns, and start making measurements. Now, one final point to make here is that this process is going to take at least an hour, more likely 2 hours for every mobile phase switch. So be prepared to take your time and keep an eye on the system and watch the whole process through. Now, in the video we're going to show a longer demonstration of this, showing the exact process with a lot more detail, but as a summary, this should cover the steps. Hi, in this video we're going to talk about how to switch mobile phases in OMNISEC from one mobile phase to another. Now, it's not a difficult operation. It just takes a bit of care, a bit of patience, and a bit of consideration. I'm hoping we can do it in an hour and a half to 2 hours. And in this particular case, this system is currently running PBS, phosphate buffered saline, and I'm going to switch it over to running THF. So not only are we switching mobile phases, but we're also switching from a salty aqueous buffer to an organic buffer. And I've chosen this because it's one of the most dangerous solvent switches. So it's one of the ones where we have to take the most care. But by applying the rules that I'm going to talk about, we should be able to do it safely, relatively quickly, and relatively easily. So the two main considerations to remember when switching mobile phases are precipitation of salt in the system, which must be avoided at all costs, and the difference in viscosity between different mobile phases. Because if we try to switch between different viscosities too quickly, then the large viscosity differences between, say, water and THF can exert too much pressure on the viscometer and could cause damage there. So in order to avoid salt precipitation, we just want to go from pure solvent to pure solvent. We want to make sure salt is absolutely excluded before we move from aqueous to organic. And to protect the viscometer from any viscosity changes, we just need to be sure we run at low or slow enough flow rates to avoid the viscometer changes being too dramatic. So if we hold those two considerations in our head at all times, then it's relatively easy to switch between different solvents. And as I say, we can do it in, say, 1 to 2 hours, depending on how slow and careful we are. So let's begin. As I said, the system is currently running with PBS as the mobile phase. It's running at 1 ml per minute, and is running nice and stably and well. And we can see that in the software. So here I have the software, and in the acquisition, actually I have a baseline monitor running currently, and it's just been running a few minutes, and you can see that the baselines are nice and stable, and everything is looking good. So we are ready to switch mobile phases. And what we're going to do, in order to go from PBS to THF, we're going to switch from PBS to pure water. We're going to purge out all the detectors, make sure we've got that whole system nice and cleaned out and removed all the salts, so there's no chance of any precipitation within any of the lines. And then once we're in pure water, then we'll switch over to THF. So let's do the water switch first. And to do that, simply stop the flow. And while I wait for that to happen, the process is going to be stop the flow, switch the mobile phase, prime the pump, and then flush the detectors out. And then we will do that with each switch of the mobile phase. So the pump is stopped, and let's take the lines out and switch out our PBS. I have here a bottle of distilled water, but DI water or HPLC grade water will be fine. So I'll set that in there. Of course, I'm going to prime the purge valve. I'm going to prime the pump first, so we'll open the purge valve. And then coming back to the software, prime the pump. The software, of course, reminds us to open the purge valve, and I've done that already, so I can click OK. And now the pump is going to wash itself out and prime itself for about 2 minutes. Okay, so the pump has finished priming itself, and we've now flushed out the degasser and the pump with just pure water. So we're going to close the purge valve, close the door. Now there's no viscosity difference, or a very small viscosity difference, between the PBS and the water. So flushing out the detectors we can do at 1 ml a minute. There's no chance of any salt precipitation or anything in this situation. We're washing out the salt, so we can afford to do that relatively quickly. So I will set the flow rate to 1 ml a minute, and just click set, and we'll hear the pump start, and the flow will get going, and I'll keep monitoring the baselines to see what happens. Just before I go any further, I will add that on the column side, I've removed the columns and the post-column filter already. So this is just the system they're flushing out. We're not concerning ourselves with anything of the columns or the filters today. So the only filter currently in the system is the post-pump filter, which is this one here. Okay, the flow is up and running, and now we've got to let the system purge out for a few minutes. So to get through the detectors, it's really only going to take a couple of minutes. For the viscometer, it's going to be a bit longer because the delay columns add about 10 minutes to the to a runtime, and they must fill up with water and they must entirely flush out as well. After that, we're going to purge the RI, purge the DP, and purge the IP to make sure that all our side and purge lines and reference cells are all flushed out and have the salt removed as well. So we're going to probably run for about 15 minutes or so like this. Then I'm going to do some purges, and then we'll come back and switch to THF. Okay, it's been about an hour, just under an hour since I switched to mobile phases. So let's take a look at the baseline monitor and see how the signals look. So let's go through them one at a time. So I'll turn off the others. So this is we'll start with the RI, and you can see it was going along fine. I stopped the flow and then I restarted the flow. And then when the water came through and changed out for the PBS, the RI signal went off scale, and it stayed there for a period of time. Eventually here I actually purged it. It came back to roughly 0. Stabilized. It was drifting a bit more. I purged it for a couple of minutes at the end, and then it seems to have stabilized since then. So that looks good. Let's look at the light scattering detectors. So again, the baselines were nice and stable. Then the water came through, and there was a little bit of noise and spikiness on both detectors. Not really a cause for concern because it passed through over a few minutes, came roughly back to baseline, and you can see those few spikes in the louds were clearing up, and it was all settling down again. So that looks good. Then we'll look at the viscometer. So the viscometer sees the slight viscosity difference between the water and the PBS. So this was the baseline. Then there was a bit of noise as I was priming the pump and setting things going. Then I restarted the pump flow. And then as the water came through, you see there was this dip in the viscometer which lasted a little while and then went back to baseline. And this was the water coming through and filling up the delay column. It's got a slightly lower viscosity than the buffer, and so there was a negative dip in the DP which continued until the delay column was full, and then it went back to baseline. And so in the viscometer, this dip, or it could be a rise, but this period in the viscometer is what we're most interested in. This has to stay nicely within the range of the viscometer, so it's not pushing the viscometer too hard and risking damaging the DP transducer. In this case, it was only about a 500 millivolt swing, so it was very, very small and posed no risk. Then we can see some other dips and spikes, and this was as I purged the detectors. So the RI purge was here, then I did a DP purge, then I did an IP purge, and then after that I did 3 more purges just of a minute or 2 each, RI, DP, IP. And then after that I've let the software run for another 5 or 10 minutes, let the baselines run for another few minutes. So having done all of that, you can see actually our baselines are stabilizing quite nicely and the system looks okay. So now we've flushed the whole system out with water. We've let it run for a good hour at a mil per minute, so 50-60 mils have gone through the system. And we've purged out all of the purge lines, the RI and the viscometer purge lines, to make sure that they are all clear of salt and there should be no salt left back in the system. That's flushing out salt is the number 1 step. We have to get rid of any salts that could precipitate when we exchange the mobile phases. So now we're in pure water, we're ready to switch to THF, and the process is going to be exactly the same. This time though, the viscosity difference between the water and the THF is far greater, and so I can't run at a mil per minute when I exchange my mobile phases. I've got to run slower. So I'm going to run at half a mil per minute to do this, and we'll see how that looks. Generally, if you ask us, we'll encourage you to do that as slowly as possible. 0.2 or 0.3 would be even better and more cautious. 0.1 mil per minute, leaving it overnight would be fine as well. I'm trying to push this through and do it a bit more efficiently, so I'll use half a mil per minute and then maybe accelerate to 1 mil per minute as the process goes on. So let's go through the same process again. First off, stop the pump. And again, while this slows down, the process is going to be stop the pump, switch the mobile phase, open the purge valve and prime the pump, close the purge valve, and then flow through the detectors. Initially, in this case, more slowly, and then once the viscometer has fully flowed out and the delay column is full of THF and has rebalanced itself, then we can purge out the different detectors. So the pump has stopped. And I almost forgot, one thing I haven't done is flush the auto sampler. So this is exactly the same. I want to prime the auto sampler and make sure that that is also flooded with water and that all the salt has been removed. So I'm actually going to do that first. So to prime the auto sampler, simply come here and click prime. Okay, so the auto sampler has been purged out as well now with pure water, again just to remove any salt. That's the important thing there. So now the pump is stopped and we are ready to switch to THF. Okay, so that's a new bottle of THF in place, and now we run through the same process. Open the purge valve and prime the pump for 2 minutes. Right, now we've primed the pump with THF. Again, we've flushed out the lines, the degasser, and the main pump. So we're going to close the purge valve. Come back to the software, and I'm going to set the flow rate this time because I'm going between solvents from one solvent to another. I'm going to set the flow rate lower this time, so I'm just going to run it at 0.5 mils per minute until the viscometer is fully purged. So let's watch that happen. So it's been about another 30 minutes since I put in the THF and started the flow. Let's look at the data and see what happened. Again, I think we'll run through the detectors individually so we can see exactly what happened in all of them. So in the RI, let's zoom out. In the RI, the flow stopped as we were priming the auto sampler. I started the flow, it came back up, and then it immediately went off scale. And that was when the THF came through. And actually, it looks like it came back on scale here, but it really didn't. It's just so extremely off scale. You see this sometimes when there's massive differences in the RI detector. That's been stable ever since, but that's because it's really not doing anything. It needs to be purged and then probably zeroed after that, but that's fine. If we bring on the light scattering detectors, now you can see again, this is the point when the new mobile phase came through. The RALs had a big spike and then it settled down. The LALs also had a very big spike and then even kind of a negative dip before it found a new equilibrium. And that's okay. This is because of the changing refractive index between the two mobile phases. As they mix in the cell and as one takes over from the other, there's really large changes in the light scattering signals. But the really important thing here is that there was no precipitation of salt in the light scattering detector, and there was no spikiness, and after the initial changeover, the LALs came back down to a nice baseline level, and it's been extremely quiet and stable ever since. So that's a really good changeover. The danger that we worry about with salt precipitation, as well as blockages of lines, is dirtying of the light scattering detector. But since this came back down onto scale and has stabilized, we know that's in good shape. It is a different level from where it was in water, and this is just a refractive index difference between the water and the THF. So most solvents each will have a different LALS kind of baseline level. The important thing is it's nice and flat, smooth, quiet. Likewise with the RALs. Those are both looking really, really good. Now let's look at the viscometer. So here I started the flow, and there was actually a huge spike in the DP when the THF came through, and this was very serious. So even though I was only running at 0.5 mils a minute, there was a huge spike which went over the 5,000 millivolt threshold. So this actually exceeded the limit, or what's the dynamic range of the viscometer. And if this happens too much for too long, it could cause damage. So what I did here was I purged it. I purged the DP, slowed the flow rate to 0.3, and then I ended the purge, and you can see the spike went up again, but then after that it came back down. So then I turned the flow rate back up to 0.5, and we got our big kind of viscometer changeover. So this was the delay column filling up with THF. So there was a big imbalance of the viscometer. Even running at 0.5 mils a minute, the signal was minus 3,000 millivolts. So it was a huge signal in the viscometer. And it stayed like this as the delay column continued to fill up. And then at the end, actually there was a big negative spike this time. So I wonder if there was a bubble running through the system or something. I purged. When it went off scale, I immediately purged the DP, and then I slowed the flow rate to 0.3, and then I ended the purge, and I let the flow continue. And you can see that the spike came through and it started to come back down to sensible levels. Once it was back on scale, I felt safe to turn the flow back up to 0.5 mils a minute, which I did, and that was this drop here. And then, as the delay column finished filling up and the viscometer was completely flushed with THF, the DP signal has returned to a nice baseline, actually just minus a couple of hundred millivolts, so it's very nice and close to zero. So I haven't done any purging of the detectors yet, but in terms of the dangerous points of the solvent exchange, we are past those 2 points. We flushed all the salt out of the system, so there was no precipitation, no blockages, and the light scattering detector stayed clean when we moved from water to THF. So there was no salt precipitation, so that was one danger averted. And the second danger is the big viscosity difference between the first and the second mobile phase, so the water and the THF. And we saw in the viscometer that there was a huge change, a huge DP signal when that THF came through, even when I was running at 0.5 mils per minute. So I purged the DP. If the viscometer goes up to 5,000, purge the DP immediately. Turn the flow rate down, give it a few moments, and then end the purge and see where that goes. Then after a period of time, the delay column was full, the viscometer was fully flushed out, and it all returned back to baseline. So the viscometer has made it through the solvent transition safely as well. Now I still need to do some purging, and I'm going to do that before I finish. But the 2 danger points are passed. So now all I need to do, I'm going to turn the flow rate up to 1 mil per minute, and then I'm going to purge the detectors, and then zero them if need be, and I'll be ready to go. So let's turn the flow rate up to 1 mil per minute, and we'll see some signals start to respond to that as the flow changes. The IP is actually off. So if I bring that detector on, you can see the IP flow rate changes, or changes with the flow rate. And I'm actually nearing the end of this baseline monitor, so I'm going to stop that. Yeah, I'll save this one for posterity. And now that's saved, I'm actually going to start another one that's just going to be an hour long. And collect that and start my purges. So I'll do that and then we'll finish off. Okay, so it's been about another 20 to 25 minutes since we last spoke. So let's have a look and see how we're getting on. Right, so I started a new baseline monitor and things were good, and here I purged the RI, and you can see that it wobbled around a bit and then it actually went off scale again, and it stayed there until the end of the purge. This was because this wasn't really on scale, it was actually just wildly off scale and it really needed purging. So there was some bit more of a changeover than we saw previously, and then it settled off scale. After 5 minutes, when that timed out, I zeroed it, and it went through the zeroing process and returned to a very nice 0. You can see since then it has been drifting a little bit. That's not uncommon when you've just switched from one to the other mobile phase. I'm not too worried about it at the moment. When after another purge, and by the time we've got some columns in and let the system equilibrate and got our samples ready to run, it's going to have had a few more hours to actually settle down, and I'm sure that will stabilize in due course. So the RI looks good. Light scattering, there was a bit of a wobble during the RI purge, but possibly flow rate related and certainly not a problem. They stabilized very cleanly, very well again, and are looking very clean. So the light scattering is in great shape. And the viscometer again, I've done some purges, and that looks really nice and stable. And it's about -130 now. So I've purged and zeroed the RI, but I've only purged the DP. I haven't zeroed it, and I'm not going to zero it again. I would generally say don't bother with the viscometer zeroing unless the signal is at least plus or minus 500 millivolts away from zero. If it's plus or minus less than that, it's fine, and you can just carry on and use it. So we've successfully switched the mobile phase in the system. We washed out all the salt, and then we flushed through new fresh water and then THF at a low enough flow rate so that the viscometer didn't go off scale. If the viscometer did go off scale, we purged DP immediately and slowed the flow rate even further. And doing that, I've been able to go from salty PBS buffer to THF in about 2 to 2.5 hours. It was about an hour to switch between each mobile phase. So if you're going between pure organic solvents, chloroform and THF for instance, you can do that in an hour. If you're going between buffers from one aqueous buffer to a different one, or from buffer to water methanol, you can go straight there without an intermediate step, and so you can do that in about an hour. But for this kind of situation, or maybe you were running DMF with lithium bromide and you want to go back to THF, flush out all the salt first with pure DMF, then switch to THF, and that's going to take a couple more hours. But if you follow those steps, your instrument should be nice and safe, and we are ready to install columns and proceed from there as we like. So I'm not going to do that in this video. This was more about just changing the mobile phase in the system. One last thing I need to do, of course, is prime the auto sampler with THF to make sure that's ready to go for when we start injecting samples.